Example 3. Use the law of sines to solve, and we're going to try and figure out what type of triangle we have. So again, let me draw my triangle. Maybe pause the video. You've seen me do this twice now. I don't think very much is going to change. We'll see. And let's see, I've been given angle B, which is 35 degrees. I'm being given side B, which is 5, and side A, which is 3. So what do I have here? I start with an angle, B, and then I go to a side, and then I go to another side. So what I'm being given here is either angle, side, side, which most textbooks don't use because it spells a word they don't want to see printed in textbooks. You will see it called SSA. Same difference, but just looks maybe more appropriate. Okay, so can I use law of sines on this? Do I have an anchor? And the answer is yes, I do. I have an anchor. It looks like B. So I'm going to say that the sine of 35 degrees over 5 is equal to, and I'm going to focus on angle A because I'm being given side A. So I'm going to say the sine of A over 3. And I think I will multiply both sides by 3. And so I think I'll switch to black here. I'm going to get the sine of A is equal to 3 times the sine of 35 degrees over 5. Now this is the first time that we haven't been able to just plug into our calculator and accept the answer. What I'm going to have to do in order to get the A by itself is take, oops, not cosine inverse, ahead of myself, but instead sine inverse. How about that? Sine inverse of whatever 3 times the sine of 35 degrees divided by 5 is. So what is 3 times the sine of 35 degrees over 5? So when I put that into my calculator, sine inverse of 3 times the sine of 35 degrees divided by 5, I get an answer for angle A of 20.1 degrees. Now, here's what you have to remember. 20.1 degrees may be one of the answers or the only answer, but we have to consider the alternative. In other words, we have to remember that when we do sine inverse, that 20.1 degrees is one of the angles that produces whatever this number is. And if you put that into your calculator, which I did, I got 0.34. Now I want you to think about the circle. We've worked with these a lot, but if you think about what we know about the unit circle, really what we're asking when we do sine inverse is what angle produces a sine of 0.34. Well, sine are my y values. There's 1/2. So 0.34 is going to be about here. Okay, and when I say about right here, I mean the sine is about right here. That height is 0.34 that I've written in red. And this is making sense that that is 20.1 degrees. However, there's another angle that would produce a sine of 0.34, and it's over on the other side in quadrant 2, right? That's also a positive sign. So I have to determine what is, from the positive x-axis, what is this angle? Well, that angle is simply going to be whatever 180 degrees minus 20.1 is. And that gets me 159.9 degrees. That is another angle that would produce a sine of 0.34. Now, is it a possibility in my triangle? Well, if I take 159.9 degrees and I add it to the 35 degrees that was given to me, I have the sum of those two angles that is larger than 180 degrees. And because I know that the sum of the angles in a triangle can't be more than 180, I am going to throw this one out. Now, I'll be honest with you, I wouldn't have gone through all this work if there weren't the possibility in later examples that we will have to consider this other option. So keep that in mind as we move through the slides. For now, however, I'm just going to say that angle A is 20.1 degrees. So let me see here. What else can I do? Angle C, it looks like, angle C is 180 degrees minus 35 degrees minus 20.1. Now, if I have a calculator in front of me, I'm not going to use 20.1. I'm going to use the actual decimal, that my calculator gave me, and then round that number to the nearest tenth. When I did that, I got 124.9 degrees. So angle C is 124.9 degrees. And now the last thing that I need to do, I'm going to use that anchor of the sine of 35 degrees over 5, and I'm going to set that equal to the sine of 124.9 degrees over C. Cross multiply, and I'll let you do the work on that. I'm going to go ahead and cut to the chase and tell you that the final answer, I think, for C is 7.15. 7.15. And then, like I was saying earlier, always make sure that you check at the end that the relationship between your angles and sides are consistent. So what I mean by that is if I look at my angles, I've got 35 degrees, I've got 20.1 degrees, I've got 124.9. Angle A is less than angle B is less than angle C. Now what I hope, if I've done this correctly, is that side A, side B, side C follow that same pattern. So side A is 3, side B is 5, and side C is 7.15, and so it checks. Example 4. Use the law of sines to solve another triangle. We're getting a lot of practice with this, but there's a lot of variations, so I want to make sure that you've got them all down. So there is my triangle. Here is A, here is B, here is C. C is going to be 15 degrees. Little c is 6, there's my anchor, and little a is 10. So what do I have? I have side, side, and an angle. I have side, side, and an angle. Remember from the last slide that we can also call this ASS, but that books typically don't do that. So actually, example 4 is the same type of triangle as example 3. So we know we can use law of sines pretty comfortably. I guess I will use my anchor, and I will say the sine of 15 degrees over 6 is equal to, I'm going to have to work with angle A because I know side A, and I'll multiply both sides by 10, and it looks like there's going to be an inverse involved, so the sine of A is equal to 10 times the sine of 15 degrees over 6. Whenever an inverse is involved, I like to take the time to actually put in 10 times the sine of 15 degrees divided by 6 into my calculator so that I can wrap my brain around what that number is. I got 0.43 approximately. So I know that what I'm looking for is the angle that produces a sine of 0.43. Now I want you to think about that. What quadrant produces a sine of 0.43? That's a positive value, so you're going to find that in quadrant 1. That's what your calculator is going to give you. But we also know that another possibility for a positive sine would be in quadrant 2. So we're going to have to do the same thing that we did on the last slide. Whenever we're dealing with an inverse, we always have to take into consideration the other possible answers. Now you might be thinking to yourself, well, why aren't you doing the plus 2 pi k thing or the plus 360 degree k thing? Well, because I'm working in a triangle, so I know I can't be larger than 180 degrees. When I put sine inverse of 0.43 into my calculator, I got 25.6 degrees, and that's a good answer. Now, another possibility for A is, let's see here, if I take 25.6 degrees and I add it to the angle that was given to me, which is 15 degrees, you're going to get, what is it, 40.6? And so I know, let me see here, I'm skipping around a little bit, but let me just, I've got 25.6 here. Looks like I've moved on to angle B. Angle B is going to be whatever 180 degrees minus 25.6 degrees minus 15 degrees is. So angle B, it looks like, is going to be 139.4 degrees. Now I skipped about. Let me come back to this or A. One thing I forgot to say is, okay, 25.6 degree angle is going to produce a sine of 0.43, but the other possibility is going 180 degrees and subtracting out 25.6. That will also give me an angle that produces a sine of 0.43, and that's 154.4. Now in the last slide we threw out the number that we got because it was too big. Well, what was given to me is 154.4 and C of 15 degrees. If I take 154.4 and I add it to 15 degrees, I am under 180. And so that means I actually have two possible measures for angle A, which tells me that there are two possible triangles in this scenario. So I'm going to start using subscripts now to help me. I'm going to say that one of the angle A's could be 25.6, but another possibility would be 154.4 degrees for a different triangle. I have a GeoGebra app that's coming up that will allow you to see what that angle might look like, or excuse me, what that triangle might look like. But for now, we're going to say, okay, we do know that we have two possibilities. We either have A sub 1 being 25.6 or A sub 2 being 154.4. If A sub 1 is 25.6, then B sub 1 is 139.4, and B sub 2 would be 180 degrees minus the 154.4 minus the 15 that was given to us. So B sub 2 would be small, but it does fit, 10.6. So let me just make a note here. I'm going to say that angle A is 25.6 or 154.4, and angle B is 139.4 or 10.6. The things that were given to me have to stay. So what I've got circled in red, those can't change. Those have to remain constant. The only thing that I have left to find, it looks like, is side B. And because angle B can be different, I'm going to have two answers for side B as well. So here's what I've got. Still going to use my anchor. I'm going to say that the sine of 15 degrees over 6 is equal to, let me deal with the 139.4 degrees over B, and I know that that 139.4 came from angle B sub 1, so this is going to be side B sub 1 as well. And when I multiply, cross multiply, and solve for B, I'll let you do that on your own. If you don't get the same answer as me, make sure that you let me know. But I got 15.07. So for side B, I'm going to have 15.07, or the other option would be, I'm going to stick with my anchor, but now I'm going to use angle B sub 2, which was 10.6, and I want to find side B sub 2. And I'll let you do this one on your own as well. And I ended up with, looks like 4.25. Shouldn't surprise me that it's so small because the angle is so small. Remember that relationship. If you have a large angle, then the side across from it is also going to be large. So those are my two possibilities. And the way that you would write that out is you would literally say, in triangle 1, these are the possible angles and sides, and in triangle 2, these are the possible angles and sides. So hopefully that GeoGebra applet confirmed in your mind that there are, in some cases, two possible triangles, and you were able to play around with those sliders, setting them to example 4, what you were given, and then hitting show ambiguous case, and you were able to see the two answers that we came up with. Let's look at another one here. What type of triangle do we have? Let me set up A and B and C. A is 50 degrees. Side A is 5. There's my anchor. And side B is 8. So I can't find the other two angles just by subtracting from 180 because I only have one angle, but I do have an anchor, so let me work with that. And so I'm going to say that the sine of 50 degrees over 5 is equal to the sine of B, angle B, over 8. And I'll cross multiply. Hopefully you're getting really good at this because we've done it several times. And so I'm going to get that the sine of B is equal to whatever 8 times the sine of 50 degrees over 5 is. Now, one of the things, like I've told you, that I like to do just to give me a feel for what's going on anytime I know that I'm going to have an inverse involved is actually put into my calculator what is 8 times the sine of 50 degrees divided by 5. And when I put that into my calculator, I get 1.23. So what this problem is asking me to do is find the angle that produces an output of 1.23 degrees. Now that should raise some bells and whistles in your head. If it doesn't, well, then this will. When you put that 1.23 into your calculator, depending on what kind of calculator or graphing device you have, it's probably going to give you an error message. And the reason for that is this. If you remember our earlier conversations regarding how or what the sine even represents, we were always working on a unit circle. And even when we graphed them, right, the graph was always between 1 and -1. So although I can put in any angle that I want, I am never going to have an output larger than 1 or smaller than -1. So expecting for me to have an angle that produces an output of 1.23 is simply not possible. By the way, what type of triangle was this? This was an angle and a side and a side, angle and a side and a side, or better known as side-side angle. And we've already seen this triangle. We saw it in example 4 giving us 2 triangles. We saw it in example 3 as giving us 1 triangle. And now we see it giving us no triangles. And so the conclusion that we can make, let me erase my screen. The conclusion that we can make is that when more than one triangle may satisfy given criteria, we describe this as an ambiguous case. Triangles that are classified as side-side angle, which we've seen 3 of those in which we know the length of 2 sides and the measurement of the angle opposite one of the given sides, may result in 1 solution, 2 solutions, or even possibly no solutions. Now, the only time that you have to worry about this is in the side-side angle.